Last time we started section 3.1 called Numeration Systems. We went through several. First, I told you about the fact that our numeration system is called what? Hindu Arabic, that's right. We talked about the Egyptians. They had all sorts of fun little drawing symbols. Pretty convenient in terms of being able to read or write it, but not super convenient in terms of efficiency, right? It could be very lengthy in writing out value. We also talked about the Babylonians, very few symbols, so that's like fabulous, but they do get repeated in awkward ways. They also have this interesting base 60 system, which is not super convenient for separating place values, and there's no zero. There's no way to represent what happens when a place value is missing, and when you have a place value system, not having a zero becomes a problem very quickly. And then we were looking at the Mayans. The Mayans had this very interesting vertical system, bars and dots. They did have a zero, which was good. So it has the ability to separate place values somewhat, but not so much when we have like duplicating bars that can't be separated by dots, what they have. And we encountered one of those last time. In particular, that one is where I think we ended. Did we stop right here? Yes, so we were ready to do the Mayan, our number into Mayan, right? Awesome, okay. So what I want you to remember briefly, I'll go through it again to remind you how we did it, is this method for turning our number into other number systems is the same method we're going to use no matter what number system we're moving into next. So we first need to know what their place values are. So for the Babylonians, we had the ones place, the 60s, 60 squared, 60 cubed, and we wrote out that 60 squared was 3,600 and that 60 cubed was 216,000. I had us do that last time as well on the Mayans out to the side in red there. I wrote out that the 20 times 18's place was the 360s. And then the 20 squared times 18 was 7,200. And then the next one was 144,000. So these are our place values that we're going to be using on this problem. So again, let me write them down really quickly here. I have the ones place. I have the 20s place, 360, 7,200, and then 144,000. I'm not writing the comma like in the middle of 144,000 because I'm separating my numbers with commas. I don't want to confuse the issue. So what we're going to do is we're first going to divide our number, 58,532, by the biggest thing it can divide by. So can I divide it by 144,000? No. 7,200. Yes, so that's the one I'll start with. I will start with a 7,200 as a divisor. Our 58,000 will be underneath sort of that top hat look. Was it 532? And we'll divide. So grab your calculator. We are looking for how many whole number times this will divide in. 8 it is. And what is 8 times 7,200? I think you mean 57. Okay. 57,600. Okay, and then we subtract. So what do we get when we subtract here? 932. Okay, now I mentioned last time that the next divisor will be the next one no matter whether it goes in or not. So the next divisor in my list, so I did this one, is 360. It actually still will go in. So I have 360. How many times will 360 go into 932? 2. Twice, yep. And what is 2 times 360? 720. And when I subtract this one, what do I get? Okay. So what will I divide by next? 20. And how many times will 20 go into 212? 10, good. That's 200 if I multiply, leaving me with 12. And my last place value is the ones place, and 1 will go into 12 times. When I subtract at the end, I get a remainder of 0. I know I'm done because I have divided by 1, and I have a remainder of 0. Those are the two flags that let me know I'm at the end of the problem. Now, these numbers over here on the side of my hats, 8, 2, 10, 12, are really what I need, but I need to use those individual numbers and to write them like they would in Mayan. So how is it, we're going to start at the top, how is the number 8 written in Mayan? Remember, here's my, yeah, 5 is the value, is a line, right? The line is the value 5, and the dots are the value 1. So I would get 8 by doing 1 line and 3 dots. So I'm going to write down 1 line, and remember, dots go on top of lines within a place value. So 1 line, 3 dots. The next value is the number 2. How do I get the number 2? 2 dots. There's no lines on that one, right? The next value is the number 10. 2 lines. And do you see a problem? How do I know that there's a distinguishing feature between those lines that I just drew and the 2 dots from the other placeholder? And the answer is I don't. There's no way to distinguish those apart. It's unfortunate, but that's where we are. Last one is the number 12. And how do I do a 12? 2 lines with 2 dots on top, which looks unfortunately a lot like the 2 and the 10 from the previous 2 number values. But that is what it is. This is the correct representation. Unfortunately, it could be confused for something else. All right?
So we're never going to have to, like, take the symbols and find the numbers?
We did on D, the previous problem.
Oh, that's right.
Yeah, we did.
I'm slow since then, I'm sorry.
But when we did this, if you'll remember, what we do is we take the number that we're given and we make the most natural assumption which we can,
Oh, okay.
which means that bars below dots divide place values. So we're not going to divide any more place values than we know for sure are there. So we're going to go with the most natural division possible and only those and go from there. Okay? All right. I mentioned we were moving into Romans last time. Romans. Where have you seen Roman numerals used? Lots of places. Can you give me an example?
Super Bowl.
The Super Bowl. That was the first one we thought of today. Fantastic. Super Bowl, yeah. Except for the one year that the Super Bowl was the 50th Super Bowl and then they didn't do it. Did you know that?
What they do?
They just called it the 50th or something. They did not use the L. L is 50. Weird, right? Yeah. Clocks. Clocks. In fact, I had you examine Rayleigh Chapel clock. If you did, fantastic. If you forgot, it's okay. We're going to talk about it in a minute. But yeah, clocks is another one, or watches, right? Where else? There's a couple of more that I've seen. I know there's one of them you've seen because you guys have all taken some English classes.
Unless it's more like chapters.
Yeah, usually like outlines or book chapters. I have a book that I'm reading to my daughter right now, and it's set in London, so apparently they wanted to make it look and feel a little older, and so all of the chapters are done in Roman numerals. You'll also see it if you do any traveling to older places like Rome or Washington, D.C. Those are places where I've been, where I've seen them marking the buildings. They'll put the demarcation on the building or on the tombstones in a really old graveyard. Just kind of interesting that they use those for dates sometimes in that way. So let's actually fill in the ones that we know, and I'll help you fill in the ones maybe that you're less familiar with. The first 3 are super common ones, so I suspect you know them. What value does that first symbol hold? It's a 1. How about the V symbol? 5 and X? 10. So those are 3 that are common all over the place. You see them used quite frequently. Anything larger than that you're dealing with are going to be things that are more like dates, like in real life, right? So what is the L?
50.
That one's 50. That's where it came about, the Super Bowl. Does anybody know what C is? It's 100. Yeah. D? It's 500. It is. And M? M is 1,000. Yeah. So if you'll look at the list of values, you should notice some patterning going on there, right? It's all based on 1s and 5s. Agreed? Yeah, they're all there. They also do a couple of other interesting things. One of them that you're probably familiar with, and one of them that you're probably not. So the one that you're familiar with is the subtraction property, probably. To avoid repeating a symbol more than 3 times, which means they don't repeat a symbol 4 times, 5 times, 6 times. A smaller value is placed in front of a larger one. Only one value smaller may appear before a larger value. I'll tell you what I mean by that in a minute. This property directly affects only 4s and 9s. So it will never affect, say, a 3 or an 8. It will only affect 4s and 9s. So for example, if we wanted to write the number 90, okay, so I'm going to flip back to my previous screen. So 90 is close to 100, right? So either you could think I'm going to write a 50 and 4 tenths. That would make 90. But the problem is that it just said over here, I'm not going to write numbers more than 3 times. So I can't do 50 and 4 tenths. I know that adds up to 90, but that's not how they would have written 90. So what would they have done instead? Well, they would have used the symbol that's larger, the 100 symbol. But if they used the 100 symbol, then they'd have to take away 10, right? That would make the number 90. So over here, they do the 100 symbol, which is what? C, and to represent that they're taking away 90, they put the X in front of the C, in front of the 100. So because the smaller value is becoming before the larger value, that's a subtraction value. It's 10 subtracted away from 100. That gives me 90. But 99 wouldn't work like that, at least not directly. In particular, we need to think of 99 as 90 and 9. So again, how do I get 90? Well, I just did that. That's XC. That's 90. How would I get 9? You probably know that one. What's 9? IX. Yeah. So it's a 1 in front of a 10. That's 9. And what we all really love to do is what? We would love to do IC. I cannot. Because I didn't make the rules and neither did you. The Romans did. Right? If we're working within their system, we have to work within their system the way they did. And they didn't do it like that. So this is what it means up here when I said only one value smaller may appear before a larger value. So let me go back to my list of values to show you what I mean. The hundreds and the 50s can only be decreased by 10. Okay? Let me try to change color here. The 10 and the 5 can only be decreased by 1. The 500 and 1,000 can only be decreased by 100. They can only be decreased by one value beneath them. Okay? To me, the easiest thing to do is to separate it out by place value like this to remind myself. 99 is 90 and 9. How do I write 90? How do I write 9? And we'll do another one here in a minute, and we have to think about it in the same way. But that's how they do it, so that's how we're going to proceed. Okay? Now, here's the thing, kind of like when we did with the Babylonians. Great for numbers up to 1,000-ish, right? What happens if the number gets considerably larger than 1,000? What do we do then? Well, when we did the Babylonians and when we did the Mayans, what we did is we did this division algorithm business because they had a place value system, right? But the Egyptians and the Romans don't have place value systems. They just have this repeating digits that look different thing going on. And they repeat in different ways, but there's actually a lot of similarities. So what do we do when the number gets really big? Well, they have a multiplication property. When they have this happen, a large number, they put a bar on top of a Roman numeral to multiply it by 1,000. A double bar multiplies by 1,000,000. So what would we do? Well, the first thing we would do is anytime we had a number that's really bigger than 3,000. The reason I say 3,000 is because 3,000 is just 3 m's, right? That's 3,000. So 3,000 is no problem. But once I get to 4,000, I have a problem. The problem is that I can't write 4,000s down, but I don't have a bigger symbol. So what do I do? Well, 9,000 is a good example of that. So anytime we're bigger than 3,000, we can break it apart again by place value. The 9, we know how to write 9. How do I write just 9? IX. And the way that I make it 9,000 is that I put a bar on top of IX. That means 9,000. And if there were any other digits over here, like let's say that there were some numbers there that weren't zeros. There was like a 6 and a 2 and a 4. That's okay. Then I'd write out whatever's coming next. It just wouldn't be underneath the bar. Okay? I don't have that on this particular part, but that's what I would do. I'd still write those numbers out. They just wouldn't be underneath the bar. Okay, and again, if the number's bigger than that, if the number is in the millions, we do double bars. So if I end up doing something where I had an IX with 2 bars like that, that's what a double bar looks like. That's 9 million, because a double bar means million. And you can have double bars and single bars in the same problem. So like I could have, just for fun, let me write down this. That's not a good example, but this will work. This would be 9 million and then 5,000. Because it's a 5 with a 1,000 bar. I mean, and we could do this. 9,000,005,001. That's what this would be. So you'll notice that the bars sort of separate the 3-digit pieces that we have in our system, right? Very much so, in fact. All right, so let's actually take a look at a Roman numeral and do some manipulation. All right, so this is MCMX. And just like when we were working with the other numeration systems on these questions, the numeral that comes before, the numeral that comes after, the digit that we need to look at is the smallest digit. And on the Romans, that's the digit on the far right, just like it was for the Egyptians and the Babylonians. On the Mayans, it was the digit on the bottom. So if I'm manipulating something to go one less or one more, I always look at the smallest value that I do that with. Just like in our system, it's far right as well. So what does that X represent at the end? 10. So if I want it to be 1 less than that, that would be the number 9. And how do I write a 9 in Roman numerals? IX. So the part that's circled in blue is being replaced with IX, and everything else stays the same. MCMIX. That should be a McDonald's treat, a McMix. All right. Next one. The next one says the number after. So again, the 10's at the end. What would be after a 10? 11. So how would I represent that for the Romans? XI. So the symbols are actually the same, but the order is quite different, and it means something different too. MCMXI. And then what is this value in Hindu Arabic? So we have CMX, the original number. And I'd like for us to just write down what each of the symbols' number value is. So what is an M worth? 1,000. What's a C worth? 100. An M is worth, again, well, there's 1,000. We already did that one. And an X is worth 10, as we said before. So we will have a subtraction property when a smaller number comes before a larger one. And does that happen here? Yeah, it does, right here. The 100 is coming before the 1,000. So the number at the beginning, 1,000, is just 1,000. But the number that's being circled in blue, where a smaller one comes before a larger one, we subtract. So what will it be, Brianna? 900, you got it. And then the X at the end is 10. So this is actually 1910, which is a legit date if you were on the East Coast looking at a building. Okay. Now we're going to take a fun big one, because I really wanted you to see how it plays out with a large number. Okay, so I mentioned on the previous couple screens ago that separating where our commas are is a really good way to separate, and it is. Okay? However, on this one, because this is a 1, I actually only need to separate it here, because this number could be written, ignoring the 019 at the end, if the number were just 1492, it could be written with, one more back, those symbols. Right? If I had the number 1,492, I can write it with these symbols. So how would I write the 1,000 with those symbols? M, yep. How would I write 400? C, D. We didn't see that one before, right? The 100 before the 500 would give me 400. Good job, Holly Ann. How about the 90? Because the 9 is in the 90 spot. X, C. We saw that one earlier too, actually. Yeah, X, C. And then how would I write a 2? 1, 1, right? Yeah. But all of that is really not the number 1,492. It's 1,492 thousands, right? It's in the thousands place. So there's a bar on top of it. Make sure that's very clear what the bar is on top of. Because I have more numbers that follow. It's the number 19, all right? So please don't confuse things. This is a 10 and a 9, right? So how do I get a 10? X. And how do I get a 9? IX. So here's the question of the day. Oh, I forgot to bring my base 10 blocks. The question of the day, what's wrong with the clock on Rayleigh Chapel? Okay, so your homework then, when you leave today, is to try to get a good look at Rayleigh Chapel and tell me what's wrong with the clock on Rayleigh Chapel. If you find out, don't tell your classmates. Let them figure it out too. Don't go spoiling the fun. You understand? No spoiling. Okay, let's move on into the next section then. Base 10 blocks. I'll bring my actual base 10 blocks next time. I just didn't realize that I was there, I guess. Yes, ma'am.
On the last number, don't we need to put another line just to make it?
We don't. That's a good question. I'm glad you asked it, though. The reason we don't is because this is a 1. If the number here had been a 4, it would be different, because I can write the 1 in that location as part of the number 1,492.
Okay.
But if it had said 4,492, I couldn't do that, because I would have to write 4 M's, and we don't write number 4 times. So if the number had instead been 4,492, 019, like this, then this 4 would actually have to be separated here, and it would have to be written as IV with 2 lines. And then the rest of it would follow. 400 would be CD, 90 would be IX, the 2, and then it would be over 1,000, and then I'd have my 10, which is XIX. But it's simply because the number is able to be done without going any bigger. Okay, good question. All right, base 10 blocks. I am sure you have seen base 10 blocks before. If you know what I mean by that and you know you have, just raise your hand real quick. Okay, I will guarantee that the rest of you have seen them somewhere too. Base 10 blocks are a visual representation usually used in early grade school for children in understanding the difference between, say, 20 and 2 or 220 and 2. And it has to do with size. So I'll bring them in, like I said, next time. But when we're looking at them sort of in flat view, a unit looks like a little bitty square. Okay? And because it's base 10 blocks, a long would look like 10 little squares all stuck end to end like Legos. There'd be 10 of them. So this would represent a long, or a long would represent the number 10. I'm not going to draw them all in, but I probably can draw this one in. 1, 2, 3. Oh, that's terrible. We'll make it shorter and it'll be less terrible. Okay, there's a long. When you're drawing them, you can just draw a long without drawing them in like I just did, but they are 10 long, okay? A flat is actually a 10 by 10, so it looks like a big old giant grid. 10 rows, 10 columns, hence it's worth 100, right? So a unit is worth 1, a long is worth 10, there's 10 little blocks. A flat is worth 100 because there's 100 little blocks. And then an actual block, I should say 100 little units, an actual block is 3-dimensional. That's not perfect, but it's not too bad. So imagine our 3 dimensions there, right? So how much is a block worth? 1,000. So you might think, why does it matter? Well, this gives very good, clear pictures of why when I add 20 plus 30, I can combine them because they're all represented by longs. But if I add 20 plus 3, I can't combine the 2 and the 3. Are you with me? I would have 2 longs and I'd have 3 units, but I can't say 2 and 3 is 5. Are you okay? So it gives clear, distinct place values for what I'm doing. When I bring them in next time, I'll also bring in base 3 blocks so that you can see that there's really nothing special about base 10 except that we use base 10, so we think about base 10 blocks. But you can do it with any base. So in that sort of movement, we're going to talk about what happens in other bases. And again, there's a reason for this. It's because you're super comfortable with base 10. So addition and subtraction and everything else we do for the rest of the semester feel very comfortable because you're very used to it. So what I want you to get out of this section is that if we work in other bases, you might actually have to feel a little bit like your students who are not super comfortable yet with any base because it's their first exposure. So if we were looking at base 8, for example, and we were looking at longs and flats and units and blocks and so forth, a unit is still worth 1. But how many do you believe a long would be worth if you did a long in base 8?
8.
It'd be worth 8. So what would a flat be worth? 8 times 8, 64. And what would a block be worth? 8 cubed, which is, does anybody know it? 512. That's it. Good. 512. Okay. Again, imagine sticking Legos together. If you could stick them together in this way, it'd be 8 by 8, 8 by 8 by 8. We'd get 3 of them. So if you were considering manipulatives, how many units would 237, do you see that little subscript, the word 8 down there mean? It means that their base 8 blocks be worth. Well, the 2 is 2 flats. I'm going to write it out just for the sake of having done it here for a moment. 2 flats. The 3 is 3 longs. And the 7 is 7 units. But how much is a flat worth? 64. It's 2, of these pieces that are 8 by 8. They're worth 64 units individually. How much is a long worth? 8. And how much is a unit worth? 1. So if I sort of had these in Lego form and I broke them all apart into their littlest pieces, all units individually, and I counted them up the way we count in our system, how many individual units would there be? 159. Yeah. It's actually 159 units. And this is equivalent to asking, and we're going to see lots of questions asking it in this phraseology here in a moment, what would 2, 3, 7, 8 be in base 10? In base 10 means in its unit form. If I broke it all down into little bitty pieces, how many would I have in base 10? So we're going to talk about 3 bases. There's nothing special about these 3 bases. You'll encounter other bases in your homework, but these are the 3 I chose to talk about. The first one is going to be base 3, and then we're going to look at base 7, and we're going to look at base 12. So in base 10, we know that we go from 0 to 9. We did that, when Monday in class. Goes from 0 to 9, and then we go 2-digit numbers. And then when we run out of 2-digit numbers, we go to 3-digit numbers, right? The same thing happens in other bases. But there are not 10 digits in base 3. There's 10 digits in base 10. So how many digits do you think you have in base 3? 3. Yeah. The base is actually telling you how many digits you have. So if in base 10 I go from 0 to 9, and I have three digits in base 3, how far am I going to go? 0 up to what? Just to 2. There are only 3 digits. So please understand there are no 3's in base 3. Just like there's no 10 as a digit in base 10, right? We call it a word. There's a word for it, but it's not a single digit. It's a 2-digit number. So what do you suppose would happen when we run out of single digits in base 3? We have to go to 2-digit numbers, right? Just like when we run out of single digits in base 10. So what would be the smallest, do you suppose, 2-digit number? Yeah, and we call it 1, 0 to avoid the confusion. 1 and 0. Because it's a 2-digit number, smallest thing I can have in the 1's place, 0, and the next smallest thing I can have in the 3's place, because it's base 3. What would be after 1, 0? 1, 1 first, and then 1, 2. What would come next? It'd be 2, 0, and then 2, 1, and then 2, 2. And that is the biggest 2-digit number in base 3, right? So what would happen then? A 3-digit number, 1, 0, 0, and we would continue the process. I'm not going to go forever, but that's what would happen. I run out of digits faster. So what do you suppose my digits are in base 7? Yeah, 0 through 6. And then what would happen after 6? 2-digit number, and the smallest 2-digit number is? Still 1, 0. How far would I go up with 2-digit numbers in 1, 0, 1, 1? It would go up to 1, 6 before it becomes a, nope, 2, 0 next. What would how far would I have to go in general before I'd run out of 2-digit numbers? 6, 6, right? Yeah. And after 6, 6, it would become 1, 0, 0, and we would continue. What's different about base 12 than the last two? I need 12 digits, and that's more digits than I have in my own system, right? Our own base 10 system only has 10 digits, so what do we do when we run out of digits? Well, it depends on the book you use. In the book that, I'm looking at Aspen because she did contemporary math with me online, the book that we use for that contemporary math class does it differently than our book does. So here's what we do. We're going to go from 0 up to 9. And then you need a digit for 10 and I need a digit for 11, right? I need 2 more digits. The digits that your book uses is T for 10, E for 11, and if we had a need for a 12, it would use a W. But your book doesn't go any bigger than this, so you don't need to worry about what would happen when I got to 13. It just doesn't, okay? I like the other book that I use better. It uses A for 10 and B for 11 and C for 12, and that just makes so much more sense to me. Because then I can go as big as I sort of need, within reason, up to 26 more digits, right? Or at least up to O. O would not be good. That would be bad. But you get the idea. So same thing, though, here. Once I get through E, that is 12 single digits, I would go to 1, 0. And then 1, 1. And I actually would go all the way up to 1, 9. And then what would come after 1, 9? 1T, and then 1E, and then after 1E would be 2, 0. Just for fun here, how big, or what is the biggest 2-digit number? What is that? Nope. It'd be EE. Because those are my biggest single digits, so it'd be EE, and then 1, 0, 0, and so on. Yeah, EE represents that I have 11 units, right? And I would have 11 longs And how much is a long worth? 12. It is, because we're in base 12. So if I were trying to figure out, like in my last question of what is this number's unit value or base 10 value, it'd be 11 times 12 plus 11. Yeah. Yep. Super fun stuff.
So it would be bigger than like.
It'd be bigger than 99. Yeah.
But then like start back at 100.
It starts back at 100. Don't say 100. It starts back at 100. Yeah. Okay. All right. So again, when we were working with the other numeration systems, we kept asking the question, what comes before, what comes after, right? And then we asked the question, what is it in our system? So we're going to do the same thing here. What's before, what's after? So preceding means before, succeeding means after. So what number, so if I was sort of writing them in order, I need a number, and then I need 1 4 base 5. Notice we're going to write the subscript 5 to remind ourselves that we're in another base, and then the one that comes after. So what comes before 1 4? 1 3. Again, base 5. What would come after 1 4? 2 0. Why isn't it 1 5? Yeah, there's no 5s in base 5. This is 2 0. You with me? Okay. Ran out. I ran out of digits. 1 5 is not a thing because there's no 5s. So I need to increase the 5s place. That would be the second place over, and change my other one to 0. What about T00? All right, well, usually the way they ask these questions is in such a fashion that the number before or the number after is easy and the other one's hard. So on this one, it's easy to find the number that comes after. What comes after T00? T01. Okay, I'm pretty good with that? Yeah, that's after. I just add 1 to it. The problem is taking 1 away from something that's got zeros in the ones place is not as easy. It's not as easy in our base. We're comfortable and familiar. What's one before 1,000? 999. We don't have to think about it, but you ask a child that, that's a really hard question. So now you get to be the child. T00. What comes before T00? Somebody give me a guess and we'll check it out. We're just all going to listen into their conversation. You guys good with that? Yeah?
Because there's 2. Because E would be the biggest before you had to go to the 3-digit number.
Okay, ladies, give me a guess.
I know.
What do you think, Hannah? ETT. Okay, so let's check it out. This would be base 12. In our system, when we think about the number, we'll think about the number 3,000 for a moment. If we want the number that comes before it, the 3 has to decrease by 1. So what comes before 3? 2. So what comes before T? E. Is that right?
Yes. No, it's not.
E comes after T, so that's not quite right. So let's fix this. So what should it be in place of where I put what should it come before a T? The 9 came before the T, so it's actually a 9 here, yeah. So the number that comes before T, because T stands for 10, is 9. And then what comes here and here? Well, let's again look at our number. So I would decrease this one to a 2. And what would happen to all the zeros if I'm going down 1? They'd all become 9s, right? Which is the biggest value in our single digits. So ours would be E's here. 9E.
Why is it E?
Because E is the biggest number in base 12, the biggest single digit number. It stands for 11. That's not an easy question, and it's not an easy question for us in our base system, or at least for our kids in our base system either. That's tough. So what we're going to look at next, and we won't quite finish this today, is that we're going to look at converting. So converting between our system and whatever other system it is, other base values. So there's two conversions. There's one conversion, which is converting base whatever into base 10. So the picture that I always want you to have in mind is that somebody brings in a giant bag of whatever object you want. I've talked about crayons before. We can talk about marbles. I don't care. They come in and they bring in bags of these things. But they're bagged up not by base 10 numerals. They're not bags of ones and tens and hundreds and thousands. They're bags of, like my base 8, bags of 8 and 64 and 512. They're that kind of bags. So you put the numbers in expanded form, right? So if I'm talking about bags of 64, I write down, oh, I have 6 bags of 64, whatever. And then you multiply them out. So let me show you an example with base 2. So in this base, I always write my digits out with placeholders. And I write the digits that I'm given, 1, 0, 0, 1. And this is in base 2. So base 2 will have powers with a base of 2. Just like our base 10 have powers that are for base 10s, right? Base 10. So this is the 2 to the 0 place. This is 2 to the 1. This is 2 to the 2. This is 2 to the 3, and we would keep going up if we had more digits. 2 to the 4, 2 to the 5, 2 to the 6, and so forth. So expanded form means taking the value times the place's value. There's a 1 into the base 2, in the place 2 cubed. There is a 0 in place 2 squared. There is a 0 in place 2 to the 1. And there is a 1 in the place 2 to the 0. That's expanded form.
So it was taking the value of what?
It's taking the value that's in the place, right? The 1 or the 0, whatever they are, times the value of the place. Right? What does 94 mean? Well, it means there's 9 tens. A 9 in the tens place. So here there's a 1 in the 2 cubes place. And then we're actually finding out what those are. Well, what is 2 cubed? Well, it's 8. These are both 0, but we'll just write them out for the sake of having done so. It's a 0 in the 4's place, a 0 in the 2's place, and a 1 in the, what's 2 to the 0? 1. Anything to the 0 power is 1. It always ends in 1s. And if I multiply 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1, what will I get? I will get 9. This is the numeral 9. So picture-wise, what happened? Somebody came into the room and they had a bag, one bag of 8 marbles and a single marble left over. How many marbles did they have? Well, they had 9 marbles. Let's try it with base 12 because it works the same way, but it feels funnier, or it just feels different, I should say. I still have in this case, I have a 3-digit number, so I'm going to do 3 placeholders. I have a T here, a 0 here, and a 0 here. And what is T worth? 10. Okay, T is worth 10. But the place values are all values with bases of 12. So 12 to the 0, 12 to the 1, 12 squared. So there are 10 12 squareds. Again, I know there's zeros, but just play along for the moment. There are 0, 12 to the firsts, and there are 0, 12 to the zeros. Well, what's 12 squared? 144. Again, I know these are zeros, but 12 to the 1 is 12. What's 12 to the 0? 1. Yeah, anything to the 0 power is always 1. It always ends with 1. The only one that actually gives me any, value here is actually 10 times 144. So what is 10 times 144? 1,440. So again, what happened? Somebody walked into the room and they had 10 bags, and each bag had 144 marbles in it. That's 1,440 marbles. Are you all with me? Okay. this is actually a pretty good place to stop. We're actually really close to done, but we need to go the other direction. We have taken we've taken somebody else's base number and turned it into our system, and we're going to go backwards next time. All right?